All right, so today we're going to expand on a little bit something that we have been doing, and that is this particular limit. So if the slope of a curve y equals f of x exists at x equals a, that is the limit as h goes to 0 of f of a plus h minus f of a over h exists, then this limit is called the derivative of f at a. So that's a new term for you, the derivative. We are going to spend a lot of time with derivatives. And by a lot, I mean basically half the year. So this is one of the two big ideas. So the derivative then is the instantaneous rate of change of a function at a point. Remember the first day we were talking about, I was showing you when you drop the ball, we could find the average velocity. Well, now we can find the instantaneous velocity, which you've already been doing. And we have a name for it. It's called the derivative. So we can also find a derivative function so that we don't have to do it at various points. For example, if you knew the rate at which, like the one Lance and I were just doing, the rate at which the ball was falling, and you wanted to know the velocity at 4 different times, you really don't want to have to go through that whole process 4 different times, right? It would be nice if you could come up with a formula for the instantaneous rate of change at any time. And so more generally, the derivative of a function f with respect to the variable x, it's always with respect to whatever variable you're working with, is the function f, and that's not a little stray mark. That is a prime symbol, f prime of x, whose value at x is f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h, provided that this limit exists. So here we're finding the derivative at a point. Here we're finding the derivative, f prime of x, more generally. We're finding a formula for the derivative. Everybody get the difference between the two? Man, it's tough to teach when you can't hear people. All right. So if f prime of a exists, we say that f is differentiable at x equals a. And students sometimes ask, why isn't it derivatable? Because you're saying you could take the derivative. Well, remember that expression that we're taking the limit of is called the difference quotient. So that's where they got the word differentiable. All right, so let's find the derivative of f of x equals x cubed. We're going to find a general formula for it rather than at some point. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's going to be the limit as h goes to 0 of x plus h quantity cubed minus x cubed all over h. Now, you guys are all pretty good at squaring things like x plus h, right? But cubing's, or raising it to the 4th power or to the 5th power is a little nastier, right? and that can be really time consuming. Let me show you a way to do this real quickly. It's a thing called Pascal's triangle. You may have seen it before. So in the middle of this space, I'm going to write a 1. And underneath it, I'm going to write a 1 and a 1. I'm going to keep doing 1s down the diagonal as I expand it. But in the middle, I'm going to add these. So 1 plus 1 is 2. Notice if I had like x plus h squared, it would be x squared plus 2xh plus h squared, right? So the next step, this is 1, 3, 3, 1. That tells me the coefficients if I'm cubing it. If I was raising it to the 4th power, it'd be 1, 4, 6, 4, 1. That makes taking something like x plus h cubed or to the 4th or to the 5th a lot faster than trying to do it by hand. So this is going to be the limit as h goes to 0 of, so I'm on this row, I'm on the cube row. So it's going to be 1x cubed plus 3x squared h plus 3xh squared plus 1 minus x cubed all over h. So that's going to be equal to the limit as h goes to 0 of, notice the x cubes are going to subtract off. I'm going to be left with 3x squared h plus 3xh squared oh, hang on a second. Sorry, this is supposed to be h, not 1. I was like, wait a minute, why do I have that? I shouldn't have that. And that should be h cubed. Sorry, let me back up to that for just a second. Do you notice how these powers always add up to 3? X cubed, x squared times h, x times h squared. So the next one's going to be h cubed. Each time the x is going down by 1 power and the h is going up by 1 power. All over h. So now I can do the division, and this will be the limit as h goes to 0 of 3x squared plus 3xh plus h squared. As h goes to 0, the second and third terms drop out, and we're left with just 3x squared. So how many of you are taking AP Physics? Just you two? Okay, so you already learned this rule, right, for taking derivatives in AP? By the old exponent, which is exactly what we ended up with here. Yes, but this is why it works. Okay, so I know that you know that rule. For now, you're not going to be allowed to use it, but eventually I will let you use it, and I'll teach you a whole bunch of other rules that you won't learn in AP Physics. Okay? All right. So an alternate definition of the derivative is this one. The derivative of the function f at the point x equals a is the limit f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. Every once in a while, this form is used, usually because it's a little easier or because someone wants to test, do you understand how this one works? So, let's do this one, and I'm going to change this to f prime at, let's do it at 9, just to do something different. So f prime at 9 is going to be equal to, we go back up to this, it's f of x minus f of a over x minus a. So that's going to be f of x, the limit, and let me start by writing it right. So it's going to be the limit as x approaches 9 of f of x minus f at 9 over x minus 9. So that'll be the limit as x approaches 9 of the square root of x minus the square root of 9, which is 3, over x minus 9. And the problem that we have here is the same problem we always have when we're doing this. If we try and substitute in 9 directly, just like if we tried to substitute in 0 directly on the other ones, you get 0 over 0, which is indeterminate. Nobody knows what that is. So we're going to have to somehow change this so that it's no longer indeterminate. And the key is here in this numerator, notice I've got a square root minus a number. What I'm going to do is multiply both the numerator and the denominator by the conjugate of the numerator. In other words, I'm going to multiply by the square root of x plus 3 over the square root of x plus 3. The reason that we do that is it's going to get rid of all the square roots in the numerator. Because when I distribute, I'm going to have the limit as x approaches 9 of the square root of x times the square root of x is x. The square root of x times 3 is 3 square root of x. Now distributing the negative 3, I have negative 3 times the square root of x is negative 3 square root of x. And the negative 3 times positive 3 is negative 9. In the denominator, I am not going to distribute. We will never distribute in the denominator on these because I'm hoping to be able to cancel something out in just a second. So that's going to be the limit as x approaches 9 of, notice these middle two terms add out. So I've got x minus 9 over x minus 9 times the square root of x plus 3. I can divide out the x minus 9s and leave a 1 in the numerator. Please don't say it's 0. When we divide that out, it divides to 1. As x goes to 9 now, the square root of 9 is 3, and I've got 1 over 6. Any questions about that? Okay. So notation for the derivatives, we've been using the f prime notation. That is Newton's, and that is like Sir Isaac Newton, yep, the one that you know from physics. That's his way of doing it. So you'll see that a lot, or sometimes you'll just see y prime. Sometimes, so these are Newtonian. It's not super important that you know that that's Newtonian. But what happened was, historically speaking, calculus was developed in England by Newton and in Germany by Leibniz at exactly the same time. They were working on it independently. Neither one knew what the other one was doing. They didn't exactly have cell phones in those days. And they both came up with the same ideas, but they had different notation for them. So as a way of honoring both men, they kept both of these. These are all Leibniz notation. And that's not the way to spell that. Hang on a second. Leibniz. I think it's L-E-I. In German, when you see two vowels together, the second one is the one that's said. So typically this is just read dy dx. And what Leibniz was saying is that it's the differential in y over the differential in x as opposed to the difference in y over the difference in x. And the reason he called them differentials is he said they were really tiny differences. So he gave them a new name. He called them differentials. So that's also the differential in f over the differential in x. Or here it's a little bit different. This is now an operator. This says take the derivative with respect to x of f of x. So when you see something like this is like an operator. This is like taking, the square root of something. This says take the derivative of f of x. So we will use those interchangeably. The only one that you almost never see is this one. The other four, you're going to see them a bunch. And you have to know that they all mean the same thing. All right. So, estimating derivatives graphically. So one of the things that is expected that you can do on the AP exam is that you can look at a graph and estimate a derivative at any point. And it's actually not hard, especially on some of these points. For example, right here, what kind of slope does that tangent line have? Yeah, it's pretty close to 0. It looks to me like it might be slightly negative, but close enough. So that's at 2. So the graph of f prime, that's going to be pretty close to 0. Where else does that same thing happen? At 4, exactly right, Irfan. Now, what we'd like to be able to do is estimate the slope at 1. So what I will do is I will draw in a tangent line that goes at least to the right 1 so I can do a slope triangle. So I'm going to try, no, that's not good. It's easier for you guys. Nope, that's not good. That's not bad. And then what I'll do is I'll draw in a slope triangle. So that goes over 1. And I'll estimate how much this goes up. So that goes over 1, and this goes up 1, 2, and a little bit. So it's a little more than 2. I'm going to say it's 2.3. It's just an estimate. It doesn't. You don't have to get crazy with this. So at 1, the slope is about 2.3. So it's 1, 2.3, somewhere about there. And then here, I'll do the same thing again. I'll draw in a tangent line. And I'm going to erase this previous one because it's kind of in the way. So at this point, the slope, and it's really easy if you use a ruler on this or some other sort of straight edge. So let's see, if I go over 1, oh, that was nice. If I go over 1, about how much have I gone up? Well, I went from here to here. It looks like about 1.5. So at 1, I'm about at 1.5. And then over here, I'll draw in another one. This one's pretty steep. Yeah, that's not good. That's better. So if I draw in a slope triangle, I go over 1. This goes down from just under 3 to a little past 1. So let's see. We'll say it's about negative 2.2. And then I just kind of stitch these together with a smooth curve. You don't want to make it bounce. You want to make it look something like that. If I'm grading those, the only thing I'm looking for is relative height. About how high does this go? If you had it going up to 3, I wouldn't count off for that. Or if you had this one going down to negative 3, I wouldn't count off for that. And is it 0 in the correct places? Is it negative throughout this region, positive throughout this region, and positive again over here? That's all we're really looking for. So don't make yourself crazy trying to find, well, is it 3.72 or 3.75? Don't get crazy about it, okay? It's just a sketch. It's an estimate. Okay, any questions about that? Okay. Now, we can also estimate a derivative numerically. So, and this is a very rough estimate. So it says use the following table of values to estimate f prime at 3.2. I've seen this on the AP exam multiple times. It's an easy question if you know how to do it. If you don't know how to do it, well, you get it wrong. And if you don't get this one right, honestly, you're probably failing the AP exam anyway. Okay? So they're asking what happens at 3.2. Well, 3.2 is somewhere in here, right? But we don't know exactly where it is. And we don't know the value of f of x at 3.2 anyway. So what we're going to do is say that f prime at 3.2 is approximately equal to the average rate of change of f on the interval from 3 to 4. Because that's the smallest interval we have that contains 3.2. If we had a smaller interval, we would use that one. So that's going to be 30 minus 26 over 4 minus 3 is 4. Am I confident that that derivative is actually equal to 4? No. But it'll be somewhere in the neighborhood. It's not going to be negative 17. Okay? Any questions? All right. Well, that is, go ahead. So we had 30 minus 26 over 4 minus 3 is 4 over 1, which is 4. It's approximately 4. Okay? That's what I was saying. This is an easy problem. Any other questions? Okay. Then that's all I've got for you today. Don't forget that you have your quiz tomorrow. I will be back tomorrow. I took a COVID test this morning and I was negative, and I don't have any symptoms. So I will be back with you guys tomorrow. So if you have questions before school, I'll be there at about 7-ish. I'll look forward to seeing you guys tomorrow. That's an excellent question that I